Hello. Again, sorry for today's issues. I'm sorry that I cannot run the seminar as it should be. But now I guess I have fixed my problems with my computer and should be okay now. So I'm recording the seminar and I hope you will see it sometime when you have some free time for it. Okay. Today we have a seminar on linear regression again, and we will discuss different interesting things like feature importance or working with trained data, test data, validation data, and some advanced techniques. And also we'll discuss regularization. It's also a very important technique. So let's start. Okay, and firstly, we'll start with simple linear regression only on one feature. We will use again the data set that we used some time ago. It's a data set on houses. We have, for now, we have only two features. One of them will be touched, and another will be the feature that will be used in our model. So we want to predict the sale price of the house. It's actually the price of the house. And also we have a feature named above ground living area in square feet. And we will try to use it for our predictions. Okay, let's load this data and then look, we can look on the result. We can see this the attached variable in our feature. If we look on some details, we can see that the ranges of these variables is rather big. For example, sale price start at 34,000 and end with much bigger values. So we have a very big range of these features. So probably it can harm somehow our predictions. Let's look on the distribution of the data. You can see here is the distribution for our feature for living area. And we can see that it's very close to normal distribution, but actually it's a bit biased. So probably we need to normalize it somehow, or maybe we should do some transformation of this feature. And then we can look on the touched feature. It's the price. We can again see that it's close to normal distribution, but it not but a bit biased. We can see a very long tail on the right. We can see very big values that are not very popular. So there are some houses that are which prices are very big, but most of the houses have much lower prices. So we can take quantity and take only rather popular values. So we won't take too much values that are bigger than this value. Also, as we can see from this plot, probably if we transform the target feature to some logarithm, for example, logarithmic scale, we can probably we will get a bit better distribution. We did last time. I think it was about 2 seminars ago. I'm not sure. Anyway, some transformations of the data is very useful technique, and I hope it will help you in some of your cases. Then let's look on the plot of the target variable and its dependence on our one feature, the learning area. We can see a very good correlation between them, but some points are rather far, lies very far from the main part. So it can be sometimes it can be hard to predict the true values. Okay, let's build our model. We build like this. We say that we have only one feature. We have some coefficient. We have constant b, and also we have some intercept, some bias. It's a, and also we have some portion of random noise, and we will build our model. We'll use not Scalon as we used it before. We will use similar package. We'll use stats models. It can also build models with models on linear regression. It's named OLC, like ordinal least squares. And it will, if we run it, we'll get results of our linear regression model. What is good in stats models packet that it can return to us a very big description of different statistics of this model that we run. So what we can see here, we can see that a rather popular metric for linear regression, R squared. Also, we can see adjusted R squared. It's like R squared, but it was adjusted to be more stable measure. But it's in this case, we can see that they are the same. That's rather good. There are some other interesting metrics. We will discuss them later, like arc and this, and it's like information, portion of information that our model can explain. Also, we can see log likelihood, and also we can see some edge statistic and scale. And the most interesting part for us now is here. We can see it's just information about coefficients around our features. Actually, we have only one feature, and another row what we can see is actually the description of the coefficient around our bias. It's this a variable. So we say that our a is equal to this value, and b is equal to this value. So our model will be with these values. So it's simply the coefficients, and then there are some descriptions on them. We can see standard error for every coefficient, and also we can see that we use some test for these coefficients. We use t-test to understand how useful these features are for our model. So we just say that we just want to know if we really want to use in our model this constant, for example, and also this feature. Actually, probably we in some cases we won't need this constant coefficient, as we have a clean dependence between the feature and our target variable. But here we can see this column. It's actually p-value. It just shows if it's rather if it's rather small, then it say that that this coefficient is useful for our model, and if this value is big, it means that this coefficient is not important for our model, and it can't help to make our prediction better. So we just should not use it in our final model. So let's say more words about this t-test. Actually, what we are testing here, there are two hypotheses. H null is, we say that we assume that our coefficient is equal to 0. And alternative hypothesis is that our coefficient is not equal to 0. And then we run our t-test. And after t-test, we will get our p-value. So it's our how we are showing in our result. And like in any other statistic test, we can choose some alpha, and if p-value is not bigger than alpha, then we will reject null hypothesis. And if p-value is greater than alpha, then we can't reject null hypothesis, and probably it means that we should consider also alternative hypothesis. It means that we should consider null hypothesis, and probably coefficient for some variable should be can be 0, and this it means that this variable is not important for our model. So about alphas, actually we know that alphas usually are used about this range. Wait, sorry. And probably the best of them is that is in the middle. Okay, let's remember what we say about hypothesis, and how we can measure the quality of some hypothesis. We know that there are different types of errors. The first type error, the first type of errors is when we say that our hypothesis is not correct, but actually the null hypothesis is correct. It's placed here. And another type, it's the second type of error. It's when we say that the null hypothesis is true, but it's actually not. And we want an easier we of course want to go to these green parts of the rectangle. But of course, sometimes we will have these two types of errors, but of course we want to minimize them. Okay, let's again let's plot the result of our model. We said that we got some values of coefficients. So our model, our result, our final model for now looks like this. Here is the intercept, and here is the coefficient for our one feature. I will have a plot like this, so we can see the predicted dependence between sale price and living area. And our predictions is in purple here. And we can see that actually we predicted our predictions rather well, but actually there are some points that are rather far from the predictions. And we can also plot we can make another plot. It's named. It's actually named residuals plot. Here we just calculate the difference between our true values and our predicted values, and plot them here. So of course, ideally, our residuals, also probably we can say that its errors, should be equal to 0. But of course, because we try to make, but of course our model can be ideal, so we won't achieve the 0 residuals, but we really want to achieve it. So we can look on the plot, and we will see our differences between our predictions and the true values. And we can see on this plot, we can see that actually there are some, in some places, the variances of these residuals are rather small. In some other places, the variances of these residuals are rather big. It means that our errors are not identically distributed. So it means that there is some, and also from the plot, we can see that there is some dependence between errors and the living error. So the more the living error, the more this variance. So it means that for some reason we didn't, our model can capture all the information from these features, and but actually we used only 2 features, so it shouldn't be any problem on the first glance. But as we remember, we can try to transform our features somehow, and probably we'll see, and probably our model will find all the dependencies much better. Let's miss this part for now, and we'll try to make a model on transformed features. So we use the same x and the same y, but we will use logarithms of them. So we use the logarithm of our feature and logarithm of our target variable. And after this, if we run our model, we will get now results. If we look on the metric r squared that we will discuss later, we will see that it became better. So it means that our model is also better. And if you look on the plot, it's a plot for our new model, we can see that plot became a bit better. It really looks close to the ideal result. And if you look on the plot of plot with the residuals, we can see that the variances of these residuals became a bit better. They became the variances became more stable. It's a good sign, but also we can see that some errors are very far, are rather big, and some errors are rather small. So of course, we can clearly see that this model is not ideal, but for now, we at least used as much information as we could from the feature living error. So it's a very good result for linear regression on only one feature. And in practice, you will never see the linear regression only on one feature. Most cases, you will see linear regression on several features. Okay, let's go back. We can look. Let's look again on this table. We can see here again the metric r squared, adjusted r squared, and what is interesting, log likelihood. We can see that it became a bit smaller than it was, but it's of course it was like this, but of course it's normal since we took the logarithm of all the features and the target variable. And if you look on the coefficients, we'll see that they also became much smaller. And also we again should look on this p-value, and we can see that both of them are zeros. So it means that they are smaller than alpha. So we can reject the null hypothesis that these coefficients are not important for our model. So we should use both intercept and this feature. As we saw from the plot, it's also a rather good model. Okay, let's discuss the r squared metric, r squared measure. It's also named a coefficient of determination. I guess you should hear something like this from your statistics course. But let's discuss it again. Actually, what it means, it just shows the portion of the explaining variance. Just the portion of the variance that our model can explain. Okay. Let's look on the formula. We can see that it's just a ratio of two things, and just SS reg and SS tot. And let's see what is it. SS reg is just explaining sum of squares. What it means? It means that it's a sum of squares of this thing. It's just y's that we predicted, and y's that is just the mean of the data that we have. So just difference between means and our predictions. And another thing, in the here we can see SS tot is just the same thing, but here is the difference between our true values and the mean of these values. So and also if we look at it closer, we can see that SS total consists of two things: this explaining sum of squares and this. This is the difference that our model is actually trying to minimize. It's just the difference between the observed data, our true values, and our predictions. So and also we can rewrite our formula like this. It's probably a better view, since we can easily understand what is SSRS. It's just the metric that we try to minimize, and then we normalize it by SS total. So it's just the ratio of our error and our mean squared error and the total error for just it's not okay. It's not error. It's actually the variance in our data. So in our data we have two things that can bias our prediction. It's just variance of the data and the variance of the error. And we try, as we can't do anything with the variance of the data, we try to minimize the variance of our error. So, for this reason, we try to use this this measure for checking the quality of our result. And in our model, in the first model, we got a result like this. So just about a half from 1, and we know that ideally we should have 1, but it's not for now. So we can easily see that our model only on one feature is not good. And also we should say that a bit better measure is R² adjusted. It's similar to this formula, but it a bit different because we try to somehow adjust this value to be more stable. And if we look on the results of this, it's better to look on this value since it can be more right than this. It can be more useful than this. But actually, in this case, we can see that they're the same, so it's not important. But if you look on the second model with logarithms, we can see, we can again see that they're the same. But, and also we can see that R² became a bit better. So our model, the second model, also by this metric, also is better than the first. So, by two measures, we can see that our second model is better. We can see it by R². We can see it by the main plot, and also the third thing, we can see it by the plot of residuals. So if you try to choose your model, you can use different methods to check how good or bad your models are. Then let's go to multiple linear regression. Now we will use several features. We will use, I guess, most of the features that we had in the data. So now we have features like, for example, overall quality, overall conditions, year of the house, year when the house was remodeled, and some information about the number of rooms or the areas of these rooms and so on. These are rather useful features probably, but of course we can see that some of these features are rather small. The values are rather small. They are all from 1 to 10. Overall quality is just from 1 to 10, and overall condition also. And some of them, like lot area, have very different values. For example, like this, it's very big. So if we try to run our linear regression model, we should use a very big coefficients for this value and very small coefficient for this value, only just to normalize them. We should remember that coefficients around the features, they show two things. Firstly, it shows the range of this variable proportion to other. And second, it shows how important this feature is for our model. It's clear that for our model, the more coefficient for any feature is, the more important, the more it will influence on our final result. So it should be shows that it's if the coefficient is big, it means that this variable, this feature is important for our model. But in case when we don't normalize our features, it's not like this. So if you try to get some insights from the coefficients that you got from your linear regression model, you always should remember that to do it, you should normalize your features firstly. Okay, let's work with this data. We can see also we here check for named values. As for linear regression, we need to don't have any non-values. Otherwise, we will have otherwise our model will not work. So we should check for them. We can do it with this function, and we see that the number of non-values is just 0. So it should be okay. Our model will work. Let's again define our model, but this time on all these features. Here we calculate some statistical parameters, but we'll discuss them later. Let's look on the results of the model for now. Firstly, we can see that R squared is rather high. It's a very good value. And if we look on adjusted R squared, we can see that that now it's different from the R squared, but also very big. It means that our model is rather good. Also for practice tasks, values around this value are rather good. So when we got something like only half from 1, it's not good. But if our model returns values like this, then it means that it's a rather good model. But of course, in toy tasks like this, probably we should try to get better quality, and we should try to get closer to 1. Okay, what we can see here also, we can see again log likelihood. It's rather big since we didn't normalize or took a logarithm of our features. We can see also number of observations. We can see the DF model is just number of degree of freedom. It's actually a number of features -1, I guess. Yes. What is also interesting, I'm not sure. If you want to know more about this statistics and other results that return stats models, you can look at yourself. You look for it yourself. But actually, the most important things here are R squared, adjusted R squared, and probably a statistic for some cases. Also, let's look on the coefficients. Here, we can see that some coefficients are rather big, and other are very small. And if you look on our p-values of t-test, we can see that this time our model returns very big p-values. So it's much better, much bigger than alpha, like any alpha that can be used in practice. So it's 2 big values, and it means that they can't reject null hypothesis. We can look again on the null hypothesis. It's like this. So we can reject the probability of that our coefficient, this coefficient can be 0. So probably for our model, this coefficient is not important. Actually, it's probably like this, as we have so many features. Why we should use some intercept? It can be strange. Yes. Let's look on other p-values. We can see, for example, lot area. Here coefficient is rather small. At the same time, the models say that actually by t-test, this coefficient shouldn't be 0. And although, so it means probably that values of this feature are actually also actually rather big. So we don't need to give it a big coefficient. And actually, if we look here, we can clearly see that it's like this. I guess this feature has the biggest values from all the table. So it's rather normal that this coefficient is rather small, although it's important for our model. And also we can see that there are some features like this, for example, that where p-value is too big, and we can see like this, or we can have look on some. Oh, okay. We can look on this value. We can if we choose alpha, that is okay. We can here we can choose alpha in several ways, and in some cases we can say that this value, this feature, is not important for our model. And if we choose different value of alpha, we can say that this feature is important for our model. So everything again depends on some parameters. There are some other features and results of statistic tests, but actually they are not very important in practice, but at least for machine learning. Of course, for statistics, these things are very important. And if you want to work with data from statistical point of view, you should consider all these things. Again, let's here are some descriptions of the things that we didn't discuss. For example, there are some metrics that shows some that are some information criterion. They show how model, for example, how much model can, how much information our model have, I guess like this. And also we have some important thing. It's F statistic. We can see it here. Also, we can see probability, just actually p-value of F statistic. And what is it? Actually, we just test if we have two hypotheses again. The null hypothesis is like this. If we didn't use all these new variables, if we just use for our model the intercept, what how well it could be. And the alternative hypothesis that we should use also additional variables, not only the intercept, and our model will be better. And we use formula like this, calculate the value, And then we will look on our p-value. P-value is just 0, so it means that we should reject null hypothesis. So additional variables in our model are important. So we should consider not only the intercept, but also some other features. In some cases, it can be a very important thing, but in practice, I'm not sure. Okay, it's actually can help in practice, but there are some rare cases, and I guess you will see if you should use it just from from the table. But mostly, since just test for all the features, it's much better to look on the p-value. Since using p-values, you can choose which features you would use. So you can say that we don't need, for example, this intercept. We don't need, I guess, this feature. We don't need also this feature, and so on. So and now we have 30 features, and after this procedure, we'll have just, I don't know, for example, about 20 features, and probably our model will be better. So we will test it, and we will see if we get better results. It's a very good procedure when you have so many features, since it's very simple to do it. Just eliminate features with big p-values. So I recommend this method. But of course, there are some other methods. We will discuss them later. Okay, we will discuss them now. The first thing is forward elimination. We will just try different number of features for our model. Firstly, we will use one feature and build our model. Then we will try to pair it with another feature, and we'll try it for some time. If we will see that some of these features, if we found a second feature that helps the model to become the best, we will use these two features. And next, we will like this, we will add also the third feature, the fourth feature, and so on. So and if we see that we have a lot of features and any other feature can't make our model better, it means that we found all the features and we can't get a better result just by choosing the features. But probably we need to transform the features, or probably do something, use another smart technique. Another type of feature elimination is backward elimination. It's opposite procedure of forward elimination. We just use, at first we use all the features for our model, then we try to eliminate any one feature. If it's good, then we should consider, when we say that this feature is not for our model, then we'll try to eliminate another feature, and in this manner we will decrease the number of features. It's I guess it's in some cases can be a more useful technique, but in some cases, if you want to have not so much features, it's better to try forward elimination. But of course, both of these methods are very time consumable, and probably it's easier to use just elimination by p-value. Also, another thing that you can do is, as you know, in linear regression, you won't, okay, you not want, you just should use not linear dependent variables. So firstly, you can just check for linear dependence of your variables and also for correlation. If you see that you have, for example, two features and they correlate between each other very good, it means that you just need to use one of them and not the another, since it can harm your linear regression model. Okay, so and another, okay, we have the third third type of idea that we can use for feature elimination. We can use regularization. It's a procedure when you just try to penalize somehow your weights. You just say that your weights shouldn't be bigger shouldn't be bigger than some other values. We can see usually we can see two types of regression: loss or enriched regression. I think you discussed it on your lecture. And this technique can help you to get better parameters of your linear model, and also after using regression with regularization, you can have the coefficients. You can have better coefficients. And looking at these coefficients, you can say that if coefficients are too small, or maybe they are zeros, it means that they are not important for model. So you can just eliminate them. But of course, you should remember that it works only if your features are normalized or have similar ranges. What we can see, let's look on the formula of regression. We can see that there's a part that is common, the Messier, mean square loss, and another part. It's just lambda and this function that shows our regularization. It usually can be of two types: L1 regularization and L2 regularization. The first type is just actually the first norm, and another type is just the second norm. So the first is the sum of absolute values of your weights, and the second is the sum of squares of your weights. So and also you can combine these types of regression. So you can just here summarize first one type of regression and add then another type of regularization. So you will have penalize the weights in both ways, but actually most of the time people use just one of them. We should remember that this coefficient lambda is very important for regularization. It controls the amount of how much the weights will be penalized. So if this value is too big, then our weights will become too small and probably will not get good results. And if it's too small, then we will not have any penalizers on the weights, and probably we also will get too bad results. as we used, for example, if we used so many features, and if we, as in the example, in the previous example, it also will use too small here, too small lambda here, we can have too big weights for features that are not really important. So our result metric will be not so good. But of course, also it's a good point here that lambda actually controls the complexity of the model. Since if we have big lambda, it means that we have very small weights, and if we have small weights, then it means then our model became simply as not important features will be not used in the model actually. So let's say more words about types of regularizations. The first is ridge regression, when we have the sum of squares of weights here. What should be important here? That actually ridge regression can just make the weights smaller. It can't make them zeros. And in loss regression, when we have here the sum of absolute values of weights, we actually can make the weights close to zero, but actually it not always minimize these weights. We can look again on the lecture. If where it was, I guess this. So here is ridge regression again. We can see our formula for minimization is like this. We can see a mean squared error and our regularization part. So the result weights will be like this. We can see this additional part. So the weights. So if we calculated the weights like it was in ordinal linear regression, will have like it will look like this. But we have this additional parameter. So our new ideal weights will be like this. They will be lesser than original, lesser than the weights we will get in unregularized linear regression. They will be divided by this thing. So it means that our new weights after regularization will be a bit lesser or a bit bigger after ridge regularization. And also we can see that ridge regularization can't turn them to zeros, as we just divide them by some values. And if we look on L1 regularization, last regularization, we here add sum of absolute values of weights. So we'll have it like this, but as you remember, taking absolute values of something means that we should consider two variants. First is when our weights are bigger than zero, and otherwise when our weights are smaller than zeros. So we have these two variants. And also we should remember that this applies only for one of weights. So we have a vector of weights, and one of them can be less zero, and some of them can be bigger than zero. So for one of them, we will get to this part, to the this formulas, and for some of them, part of them will go to these formulas. Anyway, we can see that our weights after lasso regularization can turn to zero. Can turn in zero if our weights will be in this range. And also we can change our original weights that we'll have using unregularized linear regression. They can be changed like this, but we can see that actually lasso can't change. Mostly don't make the weights bigger, much bigger or smaller, but it can make them zeros. And ridge regression can make the weights less, more or less, and but can turn them to zeros. Often lasso can be more simple, more useful for feature elimination. You can just run lasso and you will have some coefficients around some variables that are very close to zero. It means that you should just eliminate these features and not use them in your final model. And if you use ridge regression, you can do it so simple like this, but you can also look on the coefficients that are rather small. And if you normalized your original data, then it can show that these features are not important for our final model. So let's run L2 regularization, ridge regularization. We can do it like this. We can input some function ridge, we'll train it, predict, and we'll have some values. We can see again our mean squared error. And here, what is important here, we just for our model, we just split our data to train and test with this function. Here, test size is 1/3 of the all that data, and other part are train part. But there are different. But you not always should do it like this. You can add also validation part, so you can at first train your models on train, or you can train your models on train part, validate your models on validation part, and when you will find your final model, you can train, you can test it on the test part, so you will get not so biased results. And as we remember, the most important thing about there are two important things about training the models. First is underfitting, and another is overfitting. If we underfit, then it means we just need to train our model more or better or change something. And if we overfit, it means that our model is too complicated and it explains the train part too good. But we want to explain good the test part of our data. And in this case, we can see that train MSE is much lesser than test MSE, and probably it means that we have some overfitting. And if we don't want to get bad results, we can try another technique, for example, cross-validation. What we can do, we just split our data to 5 parts. And on the first step, we choose as test part the first of 5 parts of data. Like this, we train our model, test it on the test part, and we will have some value. Then we do it again. But now we will choose as test part the second of 5 parts of data. Then the third, then the fourth, and so on. So we will have after these 5 iterations, we will have 5 results after training our model. And if we take the mean value of this, the mean value of MSE after all 5 iterations, we will have some value, and it will be more unbiased than what we have here. Actually, we can see that it's rather similar to this, but we can see that this here we see that here we saw that 10 MSE is much less, is a bit less than test MSE, and here we can see that actually mean MSE after cross validation is also around the value that we get from the test part. So it means that we get more not so overfit results, so it's very good. Here, what is also important that cross validation in Scalon usually use some scoring function. And here you can't, and here you shouldn't pass just mean squared error. You should pass negative mean squared error, as this function tries always to maximize any metric that you pass to it. So you just try to sort your results by from the highest value to the lowest value. And when we use mean squared error, we try to minimize the values. So we should pass to all the functions that use cross validation negative mean squared error. Okay. Next, I'm not sure where we have this order, but okay. Next, we will go back to our model that we trained using rich regression. We can look on the coefficients that our model returned to us. Actually, it's named feature importance plot, and we can see that for some features, for example, overall quality, coefficient is rather big, so we can assume that this feature is rather important. And for example, number of cars that can be put in garage is also rather important, and so on. And also there are some features that are not important for our model, or they just have too small coefficients. And some some features that have negative coefficients, it means that their values, it means that they have negative influence on our touched variable. So it means that, for example, bedroom average, bedroom above ground, I guess, is can lead to less price of the house, but I'm not sure why it is like this, but probably I'm just not a specialist in this field in selling houses. I mean, okay, on the right we can see another plot. It's just standard deviations for all the variables. We can see that for some for all the features, and we can see that, for example, load area, for load area, the standard deviation is very big, but for other values, the standard deviations are not so big, and for some we can just look, we even can't see them on the plot. it means that we have very big difference between ranges of our variables. So we can't say much things about the actual importance of these features. So this plot, it can be, it can lead us to to wrong results. So let's normalize our features. So we'll have another plot. Here we can see that our standard deviations are all similar. So we can say that this case, after normalization, we can look on our coefficients of our model and assume that these coefficients are important for assume that these coefficients can show us some information about importance of some features. So here we again see that overall quality is a really important feature, but then we can see some other features that we didn't see here. For example, year of the house. It's clear that it's very important feature, but we didn't see it here. And also we have some features with negative importance. So this plot is much more useful. We can see, first we can see more, we can see a better plot. We can see importances of all, I guess, for all the features, even for half breadth, but it's very small, and we didn't see them here. And also, we can really say something about our coefficients after normalizing the values. And how we did the normalization? We just use standard scalar from Scalon. In just a very simple thing. It just like this. We divide. We find the difference between the actual value and the mean values, and then divide them by the standard deviation. So our standard deviation became 1, and our mean became 0. So, and what we can see from this plot, that all the standard deviations are really equal. So our normalization works well. Let's go further. We can see here another. Okay, we can see here another useful technique for better training of your models. It's not about feature importance, it's about selection of parameters for your model. Here, we try to choose the parameter for our ridge regression. It's named alpha, but actually it's just this lambda thing. So just the coefficient, the most important coefficient for regularization. So we should choose a smart. To do it, we can use method named grid search. It just goes through different values of alphas and train our models. And if after this, it will return to us the best alpha that it found. So we can see that the best alpha that found grid search is like this. So after training, I guess 20 models, our automatic technique research found some good results. Actually, we can see here that we again use cross-validation technique. We can see that 3 is equal to 5. So we have again 5 folds of data like this on this picture. And again, we passed here the scoring function. So we used negative mean squared error. So actually it's maximized the negative mean squared error, or what is equal to minimizing the mean squared error. And here we can see also that we say that alphas are equal to some log space, and it looks like this. In NumPy, you can say that you want to get values from one in some range, from one value to another. So if we run this function, we will get these results. So we just get the values from this to this, but in logarithmical space. If you use just linear space like this, we'll have these results. So we can see that between two values there are equal differences here, here, and here. So we just divided the numbers between -2 and 3 and in 20 parts, and we had values like this. But if we do it in the logarithmical space, we will get these values. We will get it like this. So we have values from actually from this value to this value. So it's very good, as we as a lot of parameters in machine learning are rather small. So we often have parameters like this, but we also want to not only test parameters from, for example, from this value to this value, we also want to test some very small parameters that we will not test if we use, for example, in space. So it's often popular to set parameters for methods like grid search using log space. And what results we'll get? We can look on the plot for all the alphas, and we can see mean cross-validation score for all the parameters. And we can see here we have a plot for positive mean squared error. So the best value would be here between 10 and within 100 and 1000. And so we, after using grid search, we got a very simple plot, and we found best value for our alpha parameter. Then let's go back to L1 regularization. In Scalon we have a function named lasso, and if we train it, we will get also some result. I'm not sure why you can see that it's named MSE, since it's just MSE, but I'm sorry for this typo. And then if we try to, we can also make another plot for residuals, but here we just calculate actually mean squared error. Okay, not mean, okay, squared error. And we can see that some errors are very big, and some other errors, and actually most of the errors are close to zero. So what we can do, we can just use quantities again, and we will remove two big values for which we got two big errors. And if we do it, we'll get much better results. This is a bit smaller than this, so just using quantities, we can get better results. And if you look on the plot, we can see that our errors lays actually actually not so far. We can see much better plot. Also, what is probably important here, that we use some mask here. We just use some Boolean. We got, after using this thing, we got a Boolean vector. So just it can look like this, or you can say that it looks like this, and so on. But we remember that in Python, true values are the same as ones, and false values are the same as zeros. So if we use this mask, we just here we just will get the values that for which values we will get the values for which mask is equal to 1. So we'll get from X train the values where R is under this quantity. It can be these masks are very popular in Python, and it's very easy to use them. Another thing that I wanted to say today, I guess the last thing, I just want to show you a good picture on regularization. It's a very popular picture, but it can be not so, but has some problems with this picture, I guess. But it's important to understand that for loss regression, we can draw loss regression, regression like this. Actually, loss regression is when we have, as we minimize the sum of our weights, but we use the absolute values. So we just say that the sum of absolute values of weights is less than some another value. So we'll have this so we'll have the plot like this on the left. And if we have ridge regression, we have squares of our weights. So our plot will be like this, at least for two weights. So we can see that it's for ridge regression, it's actually round. It's actually round. So it doesn't have any angles at the at our axis. So, and also if we draw somewhere our plot for our original function for minimizing our function, for example, our best weights will be in this place, and our function will distribute like this. So and the more closer we will be to the point with the best ways, the better we will get result. But actually, we also want to consider this our regularization, our penalizers. So we just need to find some point where our minimization of MSE and our minimization of sum of weights, of absolute values of weights, or squared values of weights will be I'm not sure how it's said. I mean that we should consider two constraints, I guess, like this. And if you consider loss regression, our constraints will be satisfied. Will be often satisfied in the angle of this figure. And if you consider the ridge regression, as it's always around figure, the ideal place where both constraints will be satisfied will be somewhere far from the from zero values of weights. And here we can see that we'll have zero weight be better too. So it's again about the fact that in loss regression we can make the weights zeros, and in ridge regression we just make them smaller. So it's important to remember, and probably this picture can help you remember this fact. I guess that's all for today. Again, sorry for today's issues. So good luck. You can send me questions anytime in the chat if you have some. Goodbye.